Now, those of you who come from a background in mathematics or who are majoring in math are probably thinking, yeah, okay, so we're going to do some proofs. This is not a big surprise, right? I mean, that's mathematics, okay? But some of you in computer science may be thinking, why in the world do we have to do proofs, right? We're computer scientists. We write programs, not proofs. So I kind of like to address that and kind of ask the question exactly what is the benefit of being able to do proofs? And it turns out that there's some really good reasons why we want to do this. The reason that we want to use proofs, another way of saying that is the reason why we want to reason formally, okay, is simply to be sure that we got things right. And I want you to think about this, okay? When we write programs, we're solving somebody's problems, right? You know, somebody has a need, for example, for an app that does a certain task, and we're helping them. And because of that, we really have an obligation, I think of it as a moral duty, to make sure that our programs actually do what they're supposed to. The way that we achieve this is through testing. If you're not testing your programs, if you're simply writing code and putting it out there for somebody else to use, you're hurting those people, right? You're not really helping them at all because there's a very high probability that there are bugs and they're going to be running into them all the time. So instead of getting their work done, they are finding your bugs. They're not happy. You won't be happy when you get all the bug reports. So at the very least, you have to do testing. And testing is a good thing, right? Testing will work a lot, okay? But it doesn't necessarily find all the bugs. In fact, one of the great computer scientists is called Edgar Dijkstra. And he had a great saying. He said that testing can find the presence of bugs, but it can never actually show the absence of bugs, right? It just means that if there are, quote, no bugs, is because you haven't found them. They're out there someplace. So we want to fix that. Now, here's the deal. Let's suppose that there's a bug in some program. Let's speak Pokemon Go, right? And the bug manifests itself in that sometimes you go into a room and you look for monsters and you just miss the monster, okay? And it's there, but you can't see it. Gosh, that's terrible, right? Yeah, but probably the world is not going to end if there's that kind of a bug. So that you might call that a harmless bug. Okay. Now there's some other bugs. Like for example, let's say that you have a computer and your computer implements division. Right. Suppose that there's a bug in the division in the computer, so that you type what's 2 divided by 3, and it comes back and it says, oh, that's 17, which of course is false. Is that really a bad bug? Well, it depends, right? I mean, just how important is division for you? How important is, computing averages, for example? Oh, geez, that might be really important. In that case, we can't afford bugs in division, right? What about some other things? Cars today, you look at a car and it has dozens of computers inside. Some of those computers might be controlling the braking system. Do we really want bugs in that kind of code? I don't think so, right? I mean, we actually want that to work. So what we see is that sometimes it's just vitally important that the programs work, right? And I want to share with you a little bit of history. I talked about division, and actually there is an instruction in the x86 chipset called FDIV, which does floating point divide. And God help us, when Intel came out with the Pentium chip, which was many, many years ago, there was a bug in the floating point divide instruction. Now, it didn't happen all the time. You were able to divide numbers, and most of the time it worked correctly. But some of them it didn't, okay? Now, by the way, how inaccurate was it? You would need like 1 out of 9 billion numbers to actually have an error, right? So it worked 99.9999999% of the time. It just didn't work all of the time, okay? At first, Intel tried to say, hey, you know what, guys? It works most of the time, so what's the problem? And then they realized that was not the way to proceed. If nothing else, you're computing your company's tax returns. Maybe you're not going to run into the bug, but maybe you are. Do you want to be liable for that? So Intel came back and said, okay, we'll replace all these chips. That was $1 billion that they lost in just that little mistake. So what can we learn from that experience? Well, number one, bugs happen, okay? You can take great care in your programs. I hope that you do. And believe me, there's bugs in them, okay? I know there's bugs in my programs. So that's something that we have to accept. I mean, even folks who work extremely hard to avoid them still make them. You know, Intel didn't just casually send out this chipset, right? You know, they had a catastrophic problem. Now, something else that you want to learn is that testing is incredibly useful, but is not sufficient, okay? So here's an example of some hard numbers about the Intel division bug. We're going to divide two 32-bit numbers. So how many different inputs are we talking about? 1.6 times 10 to the 19th. 10 to the 19th, well, 10 to the 6th is a million. 10 to the 9th is a billion. 10 to the 12th is a trillion. 10 million times a trillion? My God, that's a really big number, right? How many stars in the Milky Way? Turns out to be about 10 to the 11, right? So, you know, this is what? 100 million times more than there are stars in the Milky Way? That's a gigantic number, okay? We just don't have enough time to test. Even if we could test a division, right, in just microseconds, that's still a gigantic number. You just don't have the time for it. How about storage space? We're supposed to store the numbers and the answers so that we can compare. We don't have that kind of room. And here's the worst thing. Remember, you know, you only had like 1 in 9 billion numbers were actually wrong, right? So that means that if you do something like test randomly, you're actually not very likely to get the errors, right? So testing is not going to help this case, most likely. You can get lucky, but most likely testing is not going to help. So we need something else. We need something that gives us total assurance that what we're doing is correct. And the only way to get that is to actually prove the results. So here's kind of the way that I think about proving the results. Suppose your software doesn't matter. I'm thinking Pokemon Go here. If it doesn't matter, then don't worry about it, okay? There's a bug here, there's a bug there. It's all right, okay? And in the grand scale of things, it may be more important that you write the code quickly so that you get it in the App Store than that you write the code correctly, right? You know, because your users will complain, but they're still going to pay, they're still going to buy, and then they'll upgrade to get the bug fixes. It's all good, okay? Now, if it matters a little bit, right, not too much, but just a little bit, then for God's sakes, test, okay? Test a lot so that you have a really good reason to believe that the system works, okay? Now, suppose that it matters a lot, okay? Then testing is necessary, but it's definitely not sufficient. You need to do something different. For example, you may have to start reasoning formally about your programs. Reasoning formally, what I mean is mathematically, and what I mean is with proofs, okay? So as you reason formally, let's take something like a university system that's going to keep track of all of your credit hours that you've earned. You don't want bugs in that, do you? Right? So you certainly hope that the people who developed it have some reason to believe that the program works. And if that reason is expressed as a proof, then you too have very good reason to believe that the program works. Okay? So there's a spectrum. Sometimes it doesn't matter, and you can get away with doing nothing. Sometimes it matters a little bit. You get away with some testing. It matters more. You're going to have more testing. And then at the other end, you're actually going to have to give solid proof guarantees. That requires mathematical proof. One last little point. I say that proving software correct requires mathematical proof. A lot of these proofs are extremely tedious. They're boring. They're not necessarily difficult. They're just, so many details. Okay. So guess what's really good at doing those? Computers. So we can write computer programs that will help us with the proof process. That's one of the ideas that we'll actually explore in this class. We'll use a state-of-the-art tool to be able to reason about programs.